Okay, thinking back to the last section, we had equations such as y equals 2x plus 3. And we took and we would put in some values. We would put in some x values, and we were returning some corresponding y values. Such as, let's say that we plugged in 0 and we would get out 3. We plugged in 2, we would get out 7. We plugged in 4 and we get out 11. And we got the same type thing going on in this next section. We'll be talking about different types of relationships. And we see again here, we have the relationship y equals 2x plus 3 to where we have certain x values that are paired with certain y values. The relationships that we'll be discussing today, all of our inputs, or in this case, all of our x's are known as the set of all of these things are called our domain. And once we plug all these things in, we're going to get a corresponding what's called range value. So I want you to think of this as the domain is kind of like your input, and the range is actually what you get out when you put in those domain values. In these relationships, if you notice that each time you put in a certain domain value, you get only a single range value out of that, that's what's called a function. Again, a function is a special relationship that each domain value is paired with a special, unique range value. When you plug in 0, you don't get 3 and 4. When you plug in 2, you don't get 7 and 8. So therefore, this is called a function. Another good example of a function, think about going into a Walmart or grocery store or whatever. When you pick up an item, let's say you pick up a pack of ham. That each item that you pick up is paired with one and only one price. Each item that you pick up, none of them are going to have two different prices paired with that item. So therefore, that would be an example of a function. Now, something else, though. Think of this. What if you pick up a can of soup and it's also got the same price? Even though you notice, again, that ham doesn't have two different prices associated with it, you could have two different items that have the same price. That's fine. That's still a function. Each input, you're worried more about the inputs. Each input has a single output. You don't have $3.99 and $4.99 for ham. Okay, that would not be a function. So a function is a special relationship to where each input has one and only one, or excuse me, each input has a single output associated with it. Okay, let's look at some examples of what we're discussing here. Here you've got domains of cheetah, human, lion, chicken, and some ranges of 70 miles per hour, 28 miles per hour, 50, and 9 miles per hour. And I'm assuming we're looking at average speeds of different kinds of animals. And again, notice that cheetah has only 70 miles per hour, human only 28. Each element of your domain has one and only one, a single element of your range paired with it. So therefore, would this be a function? Yes. Here we see another relationship with capital letters being paired with lowercase letters, and we don't know what the relationship is here. It doesn't really matter. But go through your inputs. When I put in big A, I get out little a. When I put in big B, I get out little c. When I put in big C, I get out little e. But here's your issue. When your input is capital D, notice your output is lowercase b and lowercase d. So therefore, this would not be a function. Each element of the domain can be paired with only one, not multiple elements of the range in order to be a function. Okay, let's take a look at two other problems. Notice again your first problem here, your domain. When you plug in -2, you get 4 and only 4. When you plug in 2, you get 4 and only 4. Now here's something that gives people some issues. We have two different domain values paired with the same range value, which is perfectly fine. Where we have issues is when you have an input that yields two different outputs. So this would actually, yes, be a function because each input is paired with only one output. Second one, we see right the opposite. Each input is actually paired with two different outputs. When you get 9, you get -3 or 3. 0, no, it's only paired with one, but anytime there's a single occurrence, no, that will not be a function. Okay, for the next part of the lesson, let's revisit the equation y equals 2x plus 3. And I want to show you that this equation actually is a function. You take any input you want to. You can take 1, 2, 3, 4, 5. You can take any input, place those values into this function, or into this equation, which actually, like I said, is a function, and you get a single y value out. 5, 7, 9, 11, and 13. Notice there's no input values that yields two different outputs. So therefore, y equals 2x plus 3 is an equation that actually represents a function. And I know this is not all of our numbers, but you can think through, and there's never going to be a situation where you put anything in for x and get multiple y values out of it. When an equation is a function, we can use a special type of a notation called function notation. Function notation. And anytime you see this function notation, it's simply a red flag that says, hey, this equation is a function. And all we do is instead of y equals, when something is a function, we can replace that y equals with this notation of f of x. And notice I did not call that f times x. I called it f of x. And I'll show you in just a second that what that actually stands for. You can use the letter f. You can actually use any letter. You could say f of x. You could call it g of x equals. You could say h of x. The letter out front, the same way that you can use any letter instead of y, you could also, for function notation, you could call it r of x, s of x, t of x, whatever. You could use any letter there. This function notation is simply a shorthand notation. Take your y equals 2x plus 3 here. Before, we'd have to put something like when x equals 2, then we plug in 2. 2 times 2 is 4, plus 3 is 7, then y equals 7. Or we could write it as a point. We plugged in 2 and we got 7. Or we could write it in a table form. X, Y, we plugged in 2 and we got 7. Now, that exact same problem over here in function notation. If I want you to plug in 2, I can now simply state this. Instead of f of x, I can ask you to find f of 2. Notice what I've done there. I've replaced my x with 2. Instead of finding f of x is your actual y statement, that's your equation. If I ask you to find f of 2, that simply says take out the x, put in a 2. It means the exact same thing as this right here when x equals 2. So to find f of 2, you're going to simply do 2 times 2 plus 3. You're just plugging in 2. And this, f of 2 equals 7, means the exact same thing as all these. When x is 2, y is 7. When x is 2, y is 7. If I ask you to find f of 3, that simply means take out the x, put in a 3. F of 3, going back to my original equation, would simply do 2 times 3 plus 3, which would be 9. F of 4 would be 2 times 4 plus 3, which is 11. So anytime you have function notation, it's simply telling you if f of x is your equation, then f of 2 or f of 3 simply means to take out that x and put in those values. Okay, working some more problems. I've actually given you two different functions here, h of x being 3x squared minus 7x plus 1, and g of x being negative 3x plus 2. And again, on your homework, what they're going to ask you to do is they might say, let's find h of negative 1. H of negative 1, again, simply means let's take out the x and plug in a negative 1. Now, I gave you this problem to remind you of this. Here, x is being squared before it's being multiplied. Order of operations states that you must square something before you multiply it, unless it's in parentheses, and states to do otherwise. So here we have 3 times negative 1 squared. We're simply plugging in negative 1. Minus 7 times negative 1 plus 1. Negative 1 squared is positive 1, so we now have 3 times 1. Minus 7 times negative 1 and then plus 1. Cleaning all that up, that's 3 plus 7 plus 1, which is 11. I want to point something else out. The reason I knew to use the h function instead of using this g function over here is because it asks for h of negative 1. Now, if I ask you to find g of negative 1, the process is a little bit different because now, since the g is out front, that indicates that I'm using my g of x function. So I'm now going to do negative 3 times negative 1 plus 2. And we know that multiplying that out and adding, we get a value of 5 there. Okay, let's look at a couple more examples. First example says f of x equals 6. And notice it's not equal to 6x or anything like that. Just f of x equals plain old 6. So really, there's nowhere to plug anything in. So if I ask you to find, let's just say f of 3. There's nothing to plug in here. F of 3 is equal to 6. F of 4 is equal to 6. F of anything is equal to 6. So anytime you have what's called there a constant function. Anytime a function is equal to a constant number, it doesn't matter what you plug in, that value will always be 6. So you can think of that in terms as far as ordered pairs. When you plug in 3, you get 6. When you plug in 4, you get 6. When you plug in 5. When you plug in anything, you're going to get 6. If you actually look at the graph of that, where you've got 3, 6, 4, 6, and 5, 6, the graph of a constant function, I know I'm getting ahead, but the graph of a constant function would actually be a horizontal line. Now, over here, let's try something a little bit different. Let's do capital F. Let's try f of a plus 1. Not always will you plug in a number into your function. Sometimes you might be plugging in an expression like a plus 1, but you do it the exact same way. You're going to take out your x, and you're going to put in a plus 1. So right here where you have an x, you're going to take it out and make sure you put your parentheses there. You're going to plug in a plus 1 in this place. Cleaning up distributive property, get rid of parentheses. You're going to do 3 times a, and you're going to do 3 times 1. That'll be 3a plus 3, and we're going to bring down minus 4. Combine like terms, that gives you a total of 3a, and the positive 3 and negative 4 combined to give you a negative 1. So therefore, f of a plus 1 would be 3a minus 1, another expression. So you don't always have to get a numerical answer when you plug something in. Okay, next up, we're actually going to be graphing functions. And this might sound very familiar to what you did back in the previous section because let me remind you that f of x equals x plus 3 is the exact same thing as y equals x plus 3. So the way we're going to be graphing in functions is the exact same thing as what we did last section. So here we go. Make you a t-table, so you have f and y, or excuse me, x and y, which you can call f of x if you'd like. Those are replaceable. And pick any x values that you'd like. I'm going to pick, let's say, we'll do negative 1, 0, 1, and 2. We're going to plug those values in, and we know how to plug these in, so I'm going to speed up a little bit more. So when x is negative 1, I'm going to find f, what's called f of negative 1, by replacing x with negative 1, and I get 2. F of 0 would be 3, f of 1 would be 4, and f of 2 would be 5. We're, again, simply replacing our x's with those corresponding values. We plot those. These are ordered pair points. The first one being negative 1, 2, 0, 3, 1, 4, and 2, 5. Plotting those points gives us the following graph. Negative 1, 2, 0, 3, 1, 4, 2, 5. We can connect our dots now. And there is the graph of f of x equals x plus 3. Okay, let's look at something now that's actually nonlinear. And you're doing it the exact same way. Again, this is probably going to be just simply a review from the previous section. You can pick any values you would like for x. And this is a little bit different looking graph here that we're going to be doing. Let's do negative 2, negative 1, 0, 1, and 2. We might actually have to add some more values on top of those. So plugging in negative 2, and I'm going to come over here and I'm going to write it like this. Finding h of negative 2. That would equal negative 2 minus And then here we're going to have to square that as we're plugging it in. You can write it out, but I'm going to go ahead and save the step and actually square that as I'm plugging it in. Negative 2 to the second power would be 4. So h of negative 2 is negative 2 minus 4, which is negative 6. H of negative 1 is negative 1 minus negative 1 squared is positive 1, which would be negative 2. H of 0 would be 0 minus 0, which is 0. H of positive 1 would be 1 minus 1, which is actually also 0. And then h of 2. And you see a pattern here, negative 6, negative 2, 0, 0. And let's see, as we plug in 2, you have 2 minus 2 to the second power is 4, which is back to negative 2 again. So plotting these points, negative 2, negative 6 means we go left 2 and down 1, 2, 3, 4, 5, 6. Negative 1, negative 2 is left 1, down 2, 0, 0, 1, 0, 2, negative 2. And if you see the pattern there, you don't have to, but you could actually plug in the value of 3, and you're actually going to get 3, negative 6 down here. And I might have mentioned in the previous video that this is a quadratic equation. What we graph here is actually called a parabola. And if you need more points, if you wanted to plug in and see what it does in between, you could. But looks like this thing is symmetrical. You got a right side, left side symmetry here. And here's what the graph's going to look like. We're just connecting dots. We're going to go up a little bit higher there, and then we're coming back down. And that does form the graph of what we call a parabola, which we'll be studying a little bit later on. Okay, here I've got my graphing calculator pulled up to show you something on this next type problem. We've got the equation y equals x squared plus 5x minus 6. And I've graphed this on my graphing calculator to show you something. In order for something to be a function, that means that each x value must be paired with a single y value. And here, let's pick out some x values. We pick out an x value of 0 here. And it looks to me like 0 is paired with somewhere, and we can plug it in here to see exactly, but 0 is paired with negative 6. And I can actually use my trace function here. 0 is with negative 6. If I plug in 1, 1 is paired with 0 here. If I plugged in a value of 2, 2 is paired with 8, and you could also plug it in on here to see the same thing. When you plug in negative 1, it's paired with negative 10. So let's go back and once again reflect on what a function is. In a function, each x value can be paired with only one y value. And see, that's what we've actually got here. When I plug in negative 1, I get negative 10. And we could do that same table like we were doing a while ago. X, y, when I plug in negative 1, I get negative 10. When I plug in 0, I get negative 6. When I plug in 1, let me go back to my calculator. When I plug in 1, I get 0. Now, we do have a little bit of an issue here because when I plug in, let's see, this value here, 1, 2, 3, 4, 5, looks like negative 6. When I plug in negative 6, I also get 0. But remember that as far as being a function, that really doesn't matter. You can plug in two different x values to give you the same y value, but the problem occurs when you plug in a single x and it gives you two different y's. So what we've got here is actually a function. And when we have a graph, we actually have a shortcut way of determining if something is a function. And we call that a shortcut the vertical line test. What the vertical line test states is pretty much what we just covered. If there's an x value that's paired with multiple y values, what you're actually going to see on this graph is you're going to see points that are above other points. But what you've got going on here, when I plug in 0, I get a single y value. When I plug in negative 1, I get a single y value. When I plug in any of these other, I get single y values. I don't have any multiple y's that are paired with any x's. So therefore, this is a function, and the vertical line test states, if you can draw a vertical line anywhere, and it hits only one point, then that graph must be a function for that reason, because that x value where you drew that vertical line was only paired with one point. So therefore, since you got this bowl shape here, and you can draw vertical lines anywhere down through here and hit only single points, this graph would be a function. Now let me just make up some other type functions. Let's say here's your graph paper, and you've got something like this one. This also would be a function because you can take any vertical line. And let me get my vertical line tool here. You can draw a vertical line anywhere on this graph. And each and every one of those vertical lines are hitting just one point on that graph. So therefore, that would be a function. Now look at this next example though. If you have some S-looking shape here, and again, let me take out my vertical line tool here. And if I started drawing vertical lines, well, the first one that I draw, now let me draw one right here. And let's say, you know what, I missed it here, but I hit a single point here, so far I'm okay. Might be the same thing up here. I hit a single point here, and I didn't hit anything down here, I'm okay. But as soon as you draw a vertical line straight down the middle, all of a sudden you've not hit just one point, but you actually hit 3 points. Okay? Anytime you're able to draw a vertical line and hit more than 1 point, that function, or excuse me, that graph does not represent a function. Because what that states is, that tells me by looking at this graph that 0 as an x is paired with 1, 2, 3 different y values. So domain range-wise, domain range, 0 would actually be paired with 3 different y values. It doesn't matter what those y values are, but it's paired with multiple y's, therefore this would not represent a function. Okay, finally we're going to look at some applications of functions. And here you've got a graph. And we're going to call this graph function L. And sometimes notice that they'll just have the F there. They won't have the up X. It'll just be L. So what this graph represents, notice it says number of pages in the IRS 1040 instruction booklet and the different years, 1965, 75, 85. And notice that the number of pages in the 1040 book has increased over time. And the way you read these graphs is in 1965 it looked to be 20 pages. In 1975 it looked to be closer to 40 pages. In 85 it was closer to 60. And over here in 2015 you've got close to 240 pages in that IRS book. So that's how you read your graph. So one thing they could ask you is, okay, how many pages, and here's how they would write it, how many pages were in the book in 1975? And what that means is, let's find F of 1975. And again, we're plugging in 75. These are our inputs. These are our X's. These are our outputs or our Y's. Our inputs in this case is the years. Our outputs or our range values is the number of pages in the phone book. So F of 1975, the way we find that is we come over to 1975. We draw a vertical line that goes up to our graph. And to read it, we draw a horizontal line over to see where it crosses. And it looks like in 1975, F of 1975 is about 40 pages. Now, sometimes this is approximate because now if we had an equation, it would work a little bit better. But by using a graph, sometimes we might be approximate because there might have been 38 or 39. We might have been a little bit off there. If it asks you to find F of 1995, again, that's simply saying how many pages were in the phone book in 1995. So we go up to our graph, and then we go over and use a horizontal line to see that it looks that there's maybe a little bit more than 80. I'd say about 82, 83, something like that, pages in the book in 1995.